Most people think ice is slippery because it is smooth or because it reduces friction between surfaces. But that explanation feels too simple. The moment you actually step on ice and nearly fall without warning, something deeper must be happening. Something invisible under your feet that changes everything you thought you knew about. Something as ordinary as frozen water. Because when scientists look closer at ice at the microscopic level, the answer stops behaving like common sense and starts behaving like something unexpected. But before we reach that hidden world, we have to destroy the idea you already have in your mind about what ice actually is telling your body when you step on it. Because ice is not just a solid surface. And the real reason it feels slippery is something almost no one expects, not even in most textbooks. And once you see it, you cannot unsee it. This is where most textbooks quietly take a shortcut. When they explain why ice is slippery, they usually give you one of two stories. The first is pressure melting. The idea is simple. When you step on ice, your weight increases the pressure, and that pressure lowers the melting point of ice, creating a thin layer of water beneath your foot. That thin layer acts like a lubricant, making you slip. The second explanation is frictional heating. According to this idea, when your shoe rubs against ice, the friction generates enough heat to melt a tiny layer on the surface, again producing water that reduces friction. Both explanations sound reasonable, both are easy to imagine, and both appear in school textbooks as if they are complete answers. But the problem is, neither of them fully explains what actually happens in real conditions. Experiments show that ice remains slippery even when pressure is too low to cause significant melting, and even when temperatures are far below the point where frictional heat could produce liquid water. So something is missing, something important is being left out of the story, and that missing piece changes everything about how we understand ice. To see why, we need to look at how these explanations were built. Early scientists were trying to fit observations into classical physics, where solids are rigid, liquids flow, and friction is just surface roughness resisting motion. In that worldview, ice should behave like any other solid. But ice doesn't behave like other solids. It consistently violates those expectations in subtle but important ways. Instead of revising the model of matter itself, early explanations tried to adjust surface effects like pressure and heat to force ice into familiar categories. That is why pressure melting became so popular. It preserves the idea that ice is still just a normal solid, only temporarily changed by external forces. But modern measurements show that the surface of ice behaves in a far more complex way than simple melting. At very small scales, the surface of ice is not perfectly rigid. The outermost molecules are less tightly bound than those inside the crystal structure. They can move, rearrange, and even partially behave like a liquid layer, even when the temperature is well below freezing. This behavior does not require external pressure or friction to exist. It is an inherent property of the ice surface itself. That means the slipperiness is not just something that happens when you step on ice. It is already there. Waiting, the older explanations fail because they assume the surface of ice is static until something disturbs it. But in reality, the surface is dynamic, constantly fluctuating at the molecular level, even when nothing touches it. And once you accept that idea, the entire problem starts to look very different. Because now ice is not just reacting to you. It is already in a state that makes interaction fundamentally unusual. Once you start to see ice this way, the traditional explanations feel less like answers and more like approximations that were never meant to capture the full picture. They were stepping stones useful in their time, but incomplete in the light of modern physics. The slipperiness of ice is not a simple trick of pressure or heat, but a consequence of how matter behaves at its most fundamental level, where surfaces are not static boundaries but active, fluctuating regions shaped by molecular motion and quantum effects. And this realization forces us to rethink not just ice, but the way we explain everyday phenomena in general. Because if something as ordinary as a frozen puddle hides this level of complexity, then how many other simple explanations in our daily lives are also just simplified stories hiding a deeper reality beneath them? And that question is exactly where real science begins. Because every simple answer often hides a deeper layer waiting to be discovered. To really understand why ice behaves the way it does, we need to stop thinking about it as a solid surface you can simply stand on, and instead zoom into a scale so small that your intuition completely stops working. At the molecular level, Ice is not a smooth, rigid block. It is a structured arrangement of water molecules locked into a repeating crystal pattern. Each water molecule connects to others through hydrogen bonds, forming a lattice that looks stable and orderly from a distance, but becomes far more dynamic when you examine it closely. Inside this structure, every molecule is held in place by a balance of forces. But here is the key detail most people miss. The molecules are not perfectly still. They vibrate constantly. Even in freezing temperatures, they are never completely frozen in place. They are always moving slightly, oscillating around their positions in the lattice. This motion is small, but it becomes extremely important when we look at the surface of the ice, because the surface is where everything changes. At the top layer of ice, molecules do not have neighbors above them. Inside the bulk of the ice, each molecule is pulled equally in multiple directions, locked into a stable 3D structure. But at the surface, that balance is broken. The top molecules are missing bonds. They are less constrained. They are freer to move, shift, and respond to energy from the environment. This imbalance creates something unexpected. The surface behaves differently from the interior. Instead of forming a perfectly rigid boundary, the outermost layer of ice becomes partially disordered. Molecules at the surface can rearrange more easily, and in many cases, they behave in a way that resembles a liquid more than a solid. This is not because the ice has melted in the traditional sense. There is no visible puddle forming. Instead, it is a microscopic effect, a thin layer where structure breaks down just enough to allow motion. This is sometimes described as a quasi-liquid layer. But even that term can be misleading, because it suggests something separate sitting on top of the ice. In reality, it is not a separate layer at all. It is the natural consequence of how molecular bonds behave when they are no longer fully surrounded. The structure itself becomes unstable at the boundary, and that instability creates mobility. Now imagine placing your foot or a shoe on this surface. You are no longer interacting with a perfectly rigid crystal. You are interacting with a constantly fluctuating molecular interface. The moment pressure is applied, even slightly, these surface molecules respond. They shift, reorganize, and allow easier movement between surfaces. This is not a dramatic melting event. It is a subtle reconfiguration happening at scales far too small to see. And this is where the classical intuition completely breaks down. Because in everyday life we assume solids are solid and liquids are liquid. But ice at its surface exists in a kind of in-between state, not fully solid in behavior, yet not fully liquid in structure. It is a transitional regime governed by molecular imbalance rather than simple phase change. What makes this even more interesting is that this behavior is not uniform. It changes depending on temperature, pressure, and even the exact structure of the ice crystal. Some surfaces are more disordered than others. Some allow more molecular movement than others. This means that the slipperiness of ice is not a single fixed property. It is a dynamic response of a system constantly balancing between order and instability. So when you step on ice, you are not simply sliding on a frozen surface. You are interacting with a living molecular system that is constantly adjusting itself in response to your presence. The hydrogen bonds are shifting. The surface molecules are rearranging. And the boundary between solid and liquid is becoming blurred at a scale invisible to the naked eye. This is the first real hint that ice is not behaving like the simple solid we imagine. But even this explanation is still not the full story, because while molecular structure explains a large part of the behavior, it still does not completely answer why slipperiness is so consistent under so many different conditions. To understand that, we need to go even deeper, beyond structure alone, into the physics of how these molecular interactions evolve dynamically under force and motion. And that is where things become even stranger than they first appear. Once we understand that the surface of ice is not perfectly rigid, but instead partially disordered at the molecular level, the next question becomes even more important. Why does this thin, unstable region make ice consistently slippery in real-world conditions? Because slipperiness is not just about structure. It is about how that structure responds when force and motion are introduced. When you step onto ice, you are not simply applying weight. You are introducing stress into a delicate molecular system that is already near a boundary between order and disorder. At the surface, hydrogen bonds are constantly forming and breaking in a dynamic equilibrium. The moment pressure is applied, even slightly, this balance shifts. Molecules are pushed closer together, and their interactions begin to change in subtle but powerful ways. One of the key effects is pressure-induced rearrangement. As molecules are forced into tighter proximity, the local structure becomes less stable. This does not always create visible melting, but it does increase molecular mobility at the interface. In other words, the surface becomes easier to shear. And slipperiness at its core is not about melting alone. It is about how easily one layer of molecules can slide past another. But pressure is only part of the story. Motion plays an equally important role. The moment there is relative movement between two surfaces, energy is introduced into the system. This energy does not simply convert into heat in a uniform way. Instead, at the microscopic level, it disrupts hydrogen bonding networks. These bonds are already weak and constantly fluctuating at the surface. So even small amounts of energy can cause localized breakdowns in structure. This creates temporary regions where molecules behave more like a liquid, reducing resistance to motion. So instead of thinking about ice as something that melts into water under your foot, it is more accurate to think of it as a surface that continuously reorganizes itself under stress, moment by moment. This reorganization is what allows smooth sliding, even when traditional explanations like large-scale melting do not fully apply. There is also another subtle factor that becomes important here: frictional coupling at the molecular level. When two surfaces move against each other, their microscopic structures interact in complex ways. On ice, these interactions are unusually weak because the surface molecules are already in a partially disordered state. This means that instead of strong interlocking between surfaces, there is reduced mechanical resistance from the very beginning. The system is already primed for motion. Modern research suggests that this behavior is not governed by a single mechanism, but by a combination of effects acting together. Pressure slightly destabilizes the structure. Motion injects energy that further weakens local bonding. Surface disorder provides an already mobile layer. And together, these factors create a condition where friction is dramatically reduced without requiring a full phase transition into liquid water. This is why ice remains slippery even in conditions where classical explanations fail. There does not need to be a thick layer of melted water for sliding to occur. Even at extremely low temperatures, the surface retains enough molecular flexibility to allow movement. And once motion begins, the system continuously adapts, maintaining low resistance through constant microscopic rearrangement. What makes this even more fascinating is that slipperiness is not a static property of ice itself, but an emergent behavior of interaction. Ice alone is not slippery in isolation. It becomes slippery when another object interacts with it in a specific way. This means slipperiness is not a property of a single material, but a property of a system in motion. It only exists during interaction. And this idea changes how we think about physical properties in general, because we often assume that things like hardness, friction, or slipperiness are fixed attributes of materials. But at the microscopic level, these are not fixed traits. They are dynamic responses of systems under specific conditions. Ice is not inherently slippery in a simple sense. It becomes slippery because of how its molecular structure responds to stress, motion, and environmental conditions simultaneously. Even now, scientists continue to refine their understanding of this process. There is no single universal explanation that captures every detail perfectly. Instead, there is a layered picture emerging where multiple mechanisms overlap and reinforce each other at different scales. And this layered complexity is exactly what makes ice such a fascinating subject in physics. But even after understanding all of this, one deeper question still remains. If something as simple as ice requires this many layers of explanation, what does that say about the way we understand the rest of the physical world? Because ice is not an exception. It is a window into a much broader truth about nature itself. And that is where we move next. After everything we've explored, one thing should be clear. The slipperiness of ice is not caused by a single simple mechanism. It is not just pressure melting, not just frictional heating, and not just one neat physical trick you can summarize in a sentence. Instead, it emerges from multiple layers of behavior happening at different scales, all interacting at the same time. And this is where a deeper lesson appears, one that goes far beyond ice itself. In everyday life, we are trained to prefer simple explanations. We like clear causes and direct effects. We want one reason for one result. It makes the world feel stable and understandable. But nature does not organize itself according to our need for simplicity. At the microscopic level, systems are rarely governed by a single dominant factor. Instead, they are shaped by overlapping influences, competing interactions, and constantly shifting balances. Ice is a perfect example of this mismatch between human intuition and physical reality. At a human scale, it feels like a single solid surface. You step on it, and it either holds or it doesn't. But at the molecular scale, there is no single state of ice that fully defines its behavior. There is structure, there is motion, there is disorder at the surface, and there is constant response to external force. Slipperiness emerges from all of these together, not from any one of them alone. This is why simple explanations often fail in nature. They are not necessarily wrong, but they are incomplete. They capture part of the truth while leaving out the interactions that actually control the behavior. In the case of ice, early ideas like pressure melting were useful because they gave a starting point, but they could not account for all conditions. They could not explain why ice remains slippery in situations where melting should not occur, and they could not describe the microscopic reality of surface behavior. What replaces simple explanations is not chaos, but complexity organized across scales. At the smallest level, molecular interactions define local behavior. At slightly larger scales, collective effects emerge, and at the macroscopic level, what we perceive is the result of all these hidden layers combined into a single experience. Slipperiness is not located in any one layer. It is distributed across them. This way of thinking changes how we understand physical reality in general. It suggests that many everyday properties are not fundamental attributes of objects, but emergent outcomes of interactions. Hardness, softness, friction, conductivity, even temperature-dependent behavior all arise from deeper systems that do not look anything like the final effect we observe. And once you accept this, something important shifts in how you see the world. The goal of physics is no longer just to find simple answers, but to understand how complexity gives rise to simplicity at the level of experience. Ice feels simple when you step on it, but the simplicity is an illusion created by many hidden processes working together so consistently that they appear as one. This is also why scientific understanding often feels counterintuitive. It removes the comfort of single-cause explanations and replaces it with layered reasoning. But in exchange, it gives a more accurate picture of reality, one that does not depend on simplifying away important details. So the next time you encounter something that seems obvious, something that appears to have a straightforward explanation, it is worth remembering ice, because beneath that simplicity, there may be an entire structure of hidden interactions shaping the outcome in ways you cannot see directly. And often, the real story is not the simplest one, but the one that survives every layer of questioning. In the end, ice is more than just a slippery surface. It is a reminder that nature rarely behaves in a way that fits neatly into our expectations. And once you see that clearly, you start to realize that the real challenge in science is not finding simple answers, but learning to understand why simple answers are never the whole story.